G'day, I'm Cahn, and in this video, I'm talking about DCDC chargers and the 5 reasons they never seem to output full power when you'd expect them to. So say you've got a 25 amp DCDC charger, why does it never seem to put out 25 amps? To start with, a DCDC charger is basically a battery charger that has a DC input and a DC output, as opposed to an AC DC charger like the ones you'd plug into the wall. A DCDC charger takes power from one battery to charge another battery. And you might be thinking it's super easy to estimate how long that's going to take by taking the amp rating of the charger, 25, timesing that by hours, 4 hours, that's 100 amp hours and your battery is fully charged. But it's never that simple, and here's why. Some DCDC chargers are rated at 12 volts. 25 amps times 12 volts is 300 watts, which means that as the voltage of the battery you're charging climbs up, the current will drop proportionally. So if the battery's nearly full at nearly 14.6 volts, the charger is only capable of outputting around 20.5 amps. So as a demonstration, I've put together 2 identical setups here on the bench, both running the same 25 amp DC-DC charger. But the charger isn't that important in this case. What's important is that the rest of the setups are completely identical. The same wiring, the same input voltage and source. The only difference is that one battery is down around 50% state of charge and the other is up around 80 to 90% state of charge. So we'll give it 5 or 10 minutes and see which battery is pulling more current simply because the charger is power limited. Same chargers, same settings, same setup. The only difference here was battery voltage, but it just highlights that you can't estimate your charger's output based on current alone. And that right there is why 25 amps on the label doesn't always mean 25 amps to the terminals. I figured I'd also quickly touch on what this little unit here is. Now this is a shunt, and without getting too technical, basically measures the voltage of your system and the current that's flowing through these 2 posts, and then uses a bit of maths to do volts times amps equals watts. It also has a timing circuit or a clock circuit in there, so it'll actually give you amp hours and watt hours, so you can monitor your system in real time. Now this one connects to your phone via Bluetooth. There are other ones that just simply plug into an external screen and allow you to monitor your system like that. What I will say is it's super important to understand your system before you fit something like this, but I do recommend you fit a battery monitor of some kind. Whether it's Bluetooth to your phone or directly accessible so you can read it, it means that you can keep an eye on your system and understand what's actually going on. Second, you've got inefficiency and heat losses, as well as the DC-DC charger reducing its output if it gets too hot. And this is really a 2-part problem that feeds into each other. So number 1, if you have any heat losses, voltage drop or inefficiency in the wiring running to your DC-DC charger, not only are you wasting energy there, but it's actually making your DC-DC charger work harder and pull more power from the source than it really needs. Second, your DC-DC charger will heat up, and if it overheats, it will cut its charging or lower it to protect itself until it cools down. If you combine inefficiencies and voltage drop in the wiring with an already warm DC-DC charger, you're only going to compound your problems. And it's kind of like your phone popping up and saying charging paused, device too hot, and your DC-DC charger is doing the same thing. It's reducing output until it cools down. So here's the demo. I've got 2 identical DC-DC chargers running 2 identical batteries, both around the same state of charge. But one is running through about 2 meters of 16mm squared wiring, that's 1 meter of negative, 1 meter of positive, and the other through 12 meters of 8mm squared wiring, that's 6 meters of positive, 6 meters of negative. At first they behave the same, but as they keep running, you'll start to see one charger slowing down, due in part to the voltage drop on the input, but also because it's working harder and getting hotter, while the other keeps charging at full power. But even in a normal system, if you have wiring that's too long or not the right diameter, it might appear to work at first, but you'll quickly run into problems and you'll always be chasing them. Number 3 is voltage drop on the output of your DC-DC charger. If your wiring run is too long between the charger and the battery you're trying to charge, you're going to run into 2 main problems. Number 1, you've got voltage drop, inefficiencies and losses due to heat, which is just wasted energy, so it's not making it to the battery. And number 2, it means that the voltage that's actually reaching the terminals of the battery is lower than what the DC-DC charger is putting out. The DC-DC charger is programmed to put out a set voltage for different battery types, let's say 14.6 volts, but you might only be getting 14.2 or 14.3 at the terminals. That means charging is going to be slower, and may not actually be the right voltage for the battery to recharge correctly. So again, here's the demo. I've got 2 identical chargers, 2 identical setups, and 2 batteries at about 50% state of charge. One's connected directly with the DC-DC charger wiring. The other has an extra 4 meters of wire in between the DC-DC and the shunt. 2 meters of positive, 2 meters of negative. So let's check the voltage on each battery. At first, it's barely noticeable, but after 4 or 5 hours, that small drop really adds up. The battery with the longer wire charges noticeably slower. And you'll see the same inefficiencies downstream of your DC-DC charger if the wiring you're trying to use is too thin. All of these little details make a significant difference to your charging efficiency and speed. So as always, make sure that your wiring is as short as possible and make sure that it's the right diameter or gauge. Number 4 is another big one that catches people out as well, and that is the way that your DC-DC charger behaves as your battery gets closer to full. Now this is more obvious on AGM lead acid batteries, but it applies to lithium as well. As a battery charges, rising voltage and internal resistance naturally slow the current, but then at a certain point your charger's programming takes over, moving from the bulk stage of charging to absorption, also known as constant current, constant voltage. And the easiest way to see this is on a graph. So what you're looking at here is the voltage of the battery climbing. Once it hits the absorption voltage, about 14.6 volts for AGM and lithium iron phosphate, the charger switches from bulk to absorption mode. That's when the max current starts to drop. This isn't just maths, volts times amps equals watts, it's programmed behavior to prevent overheating or overcharging the battery. For example, as your battery voltage climbs and it's getting closer to 14.6 volts, your charger might still be outputting, say, 20 amps. Once it reaches that absorption voltage threshold, the charger will start to taper off. So from 20 to 15 amps, then from 15 to 10. And at that point, you're only outputting 14.6 volts at 10 amps, which is around 150 watts, or half of what you'd expect this charger to be able to output. Number 5 is not factoring in other loads, and this one catches out people all the time. If you're driving along with your 25 amp DC-DC charger, but at the same time you want to use your inverter, your fridge is running, and you might even be using your travel oven, you have to factor in that power usage as well. For example, let's just say that your charger could deliver 25 amps the whole time, and you're trying to recharge a 100 amp hour battery from 50% to full over 2 hours. But during that drive, your fridge is using 1.5 amp hours per hour, your inverter draws 5 amp hours per hour, and your travel oven pulls 10 amp hours per hour. Even though the charger is putting in 25 amps for an hour, you've also used 17 amp hours back out at the same time. That means the battery is really only charging at about 8 amp hours per hour. Instead of going from 50% to 100% like you thought, you've really only gone from 50% to about 64%. And that's why it's so important to consider your whole system and all of the loads that you want to run, because you might have done a good job of remembering everything you needed to make sure your DC-DC charger has the best chance of outputting 25 amps. But if you're pulling power elsewhere, there's no way you'll be able to get that full 25 amps into the battery. And that leads me to another point. Sometimes your DC-DC charger isn't the problem at all, it's something on the input side of the DC-DC charger. It might be your vehicle's starter battery, alternator, or even how you've wired the ignition wire. The ignition wire typically changes the behavior of the DC-DC charger, and that's usually fine in most modern vehicles. But in some older setups, it can actually push the 12 volt system harder than it was ever designed to deal with. For example, the ignition wire might turn the DC-DC charger on to full power anytime it sees a signal, so anytime the vehicle's on, or in this case, it actually changes the voltage cut in and cut out points, which essentially means that the DC-DC charger will run even if the starter battery and alternator are at a very low voltage, and that can put a lot more stress on the whole system. Now usually you wouldn't see an immediate issue, but over weeks or potentially months, it might take a little longer to start your car, or your headlights might be dim when you're driving at night. A lot of people think that your DC-DC charger might continue charging when you turn your vehicle off, and that's why you have a flat battery. But typically it's because of the extra stress while the vehicle is running of your DC-DC charger taking more power than your alternator can supply. Here's where expectations matter. If you have a low output alternator, say 60 amps, or an older vehicle, or you already have a lot of 12 volt systems running in your vehicle, you may not be able to run a big 40 or 50 amp DC-DC with a big 300 amp hour lithium bank day after day. You might have to make the decision to have a smaller DC-DC charger and smaller battery bank so that you're not putting as much stress on the rest of the components in your vehicle, or you might have to leave the ignition wire disconnected, which means that your secondary battery is only going to charge when the starter battery is at a high enough voltage, so that your vehicle is going to prioritize charging the starter battery, not your secondary or auxiliary battery. So if you want your DC-DC charger to actually deliver, then you've got to remember that it's just part of the system and it can't do it all on its own. You can't expect it to magically charge your battery at 25 amps if your wiring's too small, or you haven't accounted for your loads, or your alternator can't keep up, or your battery's almost fully charged. So the takeaway is that it's not that your DC-DC charger is faulty or failing, it's that the system determines how much power actually gets from the charger to the battery. So things like voltage, battery chemistry, heat, wire size, even input alternator voltage make a big difference and play a role. And that's the turn-away of making sure that your DC-DC charger is working as efficiently and effectively as it can within the scope of your system.